Good morning to everybody present here. My name is Yukta Karki, and I'm one of the agate interns majoring in computer science at the University of Louisiana at Monroe. Today, I'm here to give a short summary on the project that I worked on during my time here. First of all, I'd like to thank Agate for giving me this wonderful opportunity. I'd also like to extend my gratitude towards my mentors, Dr. Peters, Dr. Gillespie, and Dr. Ribner, for the invaluable guidance and support throughout my internship. Additionally, I also want to thank my coworkers, Hector, Collins, and Isaiah, for their immense support. So, have you guys ever thought about the hidden world beneath our feet? Just like how an MRI reviews the intricate details inside our bodies, we aim to uncover the secrets within the cell columns. So, I worked on a project that aims to enhance the soil column analysis by transforming a model to identify components like pores, solids, and organic matter. Initially, we used manual segmentation with ImageJ, but now we're automating the process with advanced software. Imagine transforming the tedious task of a manual segmentation into an automated, seamless symphony. We aim to make soil column scan analysis easier with efficient open source code, reducing costs, manual work, and making it more affordable and more accessible to a wider audience. So, to understand the process better, let's explore the steps involved. We started with the manual annotation of MRI scans of soil columns, next, created a 3D stack of these images to eliminate the edge errors, and finally, we implemented weights and biases to train the model, automating our image analysis. So, while my mentors provided the training model code, my task was to use the sweep configuration in weights and biases to achieve optimal results. So, taking a look from agricultural point of view, what motivates us to do this then? So, understanding soil composition aids farmers in applying the right nutrients and irrigation practices. It supports sustainable farming by managing soil health, reducing erosion, and maintaining fertility. Additionally, it enables precision agriculture by facilitating data driven decisions to optimize crop farming and field level management. This is the table of contents. So the first step is the manual annotation of the images using ImageJ Fiji application. So this involved compiling and stacking over 1,000 images from which we selected and segmented 5 of them to apply RGB color coding and thresholding techniques. This approach ensured accuracy at the pixel level, allowing us to differentiate the components precisely. During the annotation process, we observed that the organic materials remained mostly the same size, while the pores and other components were varying significantly. By using RGB color coding like red for air, green for organic materials, and white for pores, we could clearly differentiate and analyze the soil components. After manual annotation, we encountered edge like errors which could be caused by boundary artifacts, noise, blurring, inconsistent lighting, and alignment issues. So, to fix this, we stacked the 2D images into a 3D soul column representation. From the stack, we extracted the top and the bottom slices, getting a clear view from both the ends. We overlaid these slices to find common regions and then cropped the overlapping rectangular portion. This process eliminated background and edge errors, ensuring only the important parts of the soil column were kept. This is one of the videos that my mentor Devin first showed me as a sample of the annotated images. He used different colors to separate various components, which you guys can review later for a better understanding. Now moving on to the model. For training the model, we used a ResNet 101 based fully convolutional network for effective image segmentation tasks. My contribution was implementing weights and biases to optimize the model through the automated hyperparameter tuning. While I have a general knowledge about the model, it was developed by my mentors. So, weights and biases. It provides powerful tools and managing and for managing and visualizing machine learning experiments with real-time metric logging and performance tracking. One of its standout feature is the sweep configuration, which automates the hyperparameter tuning by defining a search space and running multiple experiments to find the best settings. Before weights and biases, hyperparameter tuning was manual and time consuming, often leading to suboptimal settings such as inefficient and inaccurate manual adjustment of the learning rate. So, with weights and biases, we automated the hyperparameter tuning using sweep configurations, varying learning rates, epochs, batch sizes, and scales to minimize the validation loss. This allowed us to track and compare model performance across the different runs in real time, leading to higher accuracy, better generalization, consistent outcomes, all while saving significant time. So these are the charts that we gained after the sweep configuration. So the first one is train loss over the epochs. The chart shows how well the model is learning during the training, how it fits the training data. A consistently decreasing loss shows effective learning. So the second chart shows the validation loss over the training epochs. Each line represents a different hyperparameter sweep run, allowing us to compare various configurations. Typically, decreasing validation loss indicates that the model is learning and improving in accuracy. In the chart, we see some spikes early on, which are quickly minimized, showing that the model is adjusting and learning. So we have two other charts here. So first one is the best model saved. This chart marks the epochs where the model with the lowest validation loss was saved. Each marker shows a model checkpoint with the best performance at that time, helping us track optimal configurations and epochs during the training. So the other chart shows GPU utilization during training. High utilization indicates efficient use of resources, which speeds up the training. So the next parallel plot shows the relationship between the hyperparameters and validation loss. Each line represents an experiment with different settings for batch size, epochs, learning rate, and scale. The color gradient signifies validation loss, with cooler colors indicating lower loss values. By focusing on these cooler lines, we can identify the best hyperparameter combinations for our model. Together, these charts provide a comprehensive view of our model's performance, allowing us to fine tune it efficiently. In conclusion, integrating weights and biases have transformed our model training into an efficient, automated process. This has significantly improved performance and made advanced soil analysis more cost effective. Farmers can now easily determine the best nutrient and irrigation strategies. These leads to better crop yields and more sustainable farming practices. Now, this is the end of my presentation. Thank you all for your attention. I would be so glad to answer any of the questions that you guys may have. Thank you.